This section, we're going to talk about sequences. So a sequence is basically just a list of numbers. And so the domain is going to be 1, 2, 3, 4, and so on, because that tells us which term it is. And then the range is the actual term, and those have to be a set of real numbers. Sequences can be shown as graphs, as points, where we have x equals 1, 2, 3, 4, and so on. And then also we have the values of those points, so we have the range in there. Or sequences can be shown as lists, which is how we're going to see them most often. And so then to show each term in a sequence, the nth term, we would have S sub n. This is the notation here to show what a sequence is. Sequences go on forever, so that's why we have this n going to infinity. So if we're going to write the first 3 terms of a sequence, all that means is to start at 1 and plug that in for n, and then continue on with those counting numbers. So we have 1, 3 times 1 minus 2, which is just 1. Then we have 1, 3 times 2 minus 2, and that's going to be 1/4. And 1, 3 times 3 minus 2 is going to be 1/7. Same thing here. Every time you see an n, you need to plug in the number that you're on. So here we have 2 times 1 minus 1, and then 1 to the 3rd power, which is just 1. 2 times 2 minus 1, 2 to the 3rd power, 3/8. 2 times 3 minus 1, 3 to the 3rd power, gives us 5/27. So those are the first 3 terms of that particular sequence. When you're trying to find the nth term, you're looking for the pattern. So in this first one, we have e to the n over n. Because again, each of the powers of e is going up, starting at 1 and going up by 1, and then so are the numerators, starting at 1 and going up by 1. The next one, if you take 1/3 to the n minus 1 power. The reason we have to do n minus 1 is because our first term here is, we would be to the 0 power, and n has to start at 1. The next one here, we have n squared, because we take the counting numbers, square them each time for that pattern. The next one, we have 2 times n to get the 2, 4, 6, 8 on the top. And then the bottom is, again, we have n, but we add 1 to it since n starts at 1. This one, since we have alternating signs, we do a -1, and because we start with a positive sign, it has to be n plus 1 power. The n power, n would be 1, and then we would start with a negative. And then on the bottom, we just have n. The last one shows us that we can have different terms depending on whether n is odd or even. So if n is odd, then we get 1. And if n is even, we have 1/n each time. So we say that a sequence converges if it approaches a certain number. As you go up in terms, and as your number of terms goes to infinity, the terms as you go to infinity keep going closer and closer to a number. So it takes us back to our definition of limits way at the beginning of the course, looking at infinite limits. And so graphically what we would be looking for is a horizontal asymptote as x approached infinity. So we can see in this table here, this one that we looked at in the last example converges because as we plug in bigger numbers for n, we're getting closer and closer to 2. So just like limits before, we write that, only we use the n's to show that we're doing sequences here. Again, because these are limits, they follow all the properties of limits. So anytime we have convergent sequences, we can use the constant multiple rule, the sum and difference rule, the product rule, the quotient rule, the power, and the root. So each of these is just an example of using those rules, those properties, and again, you'll get to the point where you're not really thinking about the properties, you're just going straight to the answer. But we can use the constant multiple rule here. We also want to keep in mind that the limit as n approaches infinity of 1 over n is going to be 0. Okay, we know that. And so this one we can change to this. So this gives us 2 times 0. This gives us just 3. And so we end up with 3 for that one. The second one, we know again that that's 1 over n times 1 over n times 4. So we're using the product rule and the constant multiple rule. And so since, again, each of these is 0, multiplying by 0 gives us 0. In this one here, we can split that up into 16n squared over 2n squared, which is 8, and then 3n squared over, or 3n over 2n squared, which is 3 over 2n. This part again gives us that 3/2 times 1 over n, and we know that equals 0 when the limit of n goes to infinity. So then that's going to be the limit as n approaches infinity of the cube root of 8, which is 2. We can also use the fact that if the inside function converges to a limit, then we can use that limit inside this one to do the same thing and evaluate the limit at that particular value for the limit of the inside function. So in this particular example, we can use 2 over n, the inside function, as our s sub n, and our f of x is natural log of x. Now, it's important that we show that it's continuous, okay, once we find L. So if we do the limit as n approaches infinity of 2 over n plus 3, again, this part's 0, so we get 3. So our L is 3, and this function is continuous at x equals 3. So the limit as n approaches infinity of the natural log of 2 over n plus 3 is just going to be the natural log of 3. Because again, we're plugging that into that function. You can also use related functions, because if the limit of the related function converges and you have a limit, then this sequence will also converge to that limit. So we know that the limit as x approaches infinity of 3x squared plus 5x minus 2, 6x squared minus 6x plus 5. Both of those go to infinity, so we can use L'Hopital's rule. To get this. Once again, both of these go to infinity. Use L'Hopital's rule again. And so because that limit is 1/2, then also the limit as n approaches infinity of this sequence is also going to be 1/2. Sequences can also diverge, so if the limit as x approaches infinity of that function is infinite, if the answer is infinity, then that function diverges. If it doesn't exist and it's not infinite, for example, it doesn't exist because it's an oscillating function, then we don't have any information about it, whether it converges or diverges. You could also use the squeeze theorem. So remember, the squeeze theorem for limits before was we would pick a function that was always less than the function we were trying to find the limit for, and one that was bigger, that where they would come together, where we were trying to find the limit. So since we're doing the limit as x approaches infinity, or n approaches infinity here, we would want to try to find functions that are both less than and greater than this particular function, and that both of those functions convert to the same limit as x approaches infinity. So we can choose -1 over n to be the less than function, and +1 over n to be the greater than function. Both of those, the limit as n approaches infinity is 0. And so according to the squeeze theorem, the limit of the squeezed function also has to be equal to 0. So here we can say that a sequence diverges to infinity because basically this is just saying if the numbers just keep getting bigger in the sequence, then the sequence diverges to infinity. And that leads us to this theorem about geometric sequences. So in a geometric sequence, you have some number to the power of n. And if that number to the power of n is between -1 and 1, that sequence will converge to 0. If it is equal to 1, it will converge to 1 because you just have 1 all the time. And if it is greater than 1 or less than -1, so if the absolute value of r is greater than 1, then that geometric sequence will diverge. So if we look down here, because r, the absolute value of r is 3/4, which is less than 1, then we're going to go to here, and it converges to 0. In this one, the absolute value of r is 4/3, which is greater than 1, and so this diverges. Another way we can talk about whether a sequence converges is if it has a bound from above or it has a bound from below. Then once we know that it's bounded, we can say that it converges, that there's a limit to what it can go to, that it's always going to be smaller than some number, it's always going to be bigger than some number, then it's bounded on either end there. So here we can say that this sequence is bounded from both above and below, because we can change this to this and say that that's always going to be less than 3. If we do the limit as n approaches infinity, that's going to be 3. So this number is always less than 3. And then this number is always greater than or equal to 1. Or greater than equal to, is always greater than 0. So those are our boundings. Because we know this is always going to be a positive number as long as n is 1 or above, and in our sequence n will always be a positive number. So convergent sequences are bounded. Again, that's what it means to be bounded, is that there is a limit. And if it's not bounded from above or from below, then that sequence is going to diverge. So sequences can be increasing, decreasing, or increasing or non-decreasing. So they don't have to be increasing, they can also be non-decreasing. And then they can be decreasing or non-increasing. And if any of those things are true, then the sequence is monotonic. So these are 3 different ways that you can show that a function is decreasing or increasing. You can use the algebraic difference. If you subtract 2 terms that are next to each other in your sequence and you get a number that's less than 0, then your sequence is decreasing. If you get a number greater than 0, then that sequence is increasing. So that makes sense. If we do the algebraic ratio test, then we take 2 terms that are next to each other and we make a ratio for them. This has to be true as long as the term is positive. And if that term is positive, then if we take the term after it and make a ratio of those 2 and we get 1, then we know that we have a decreasing, or less than 1, then we have a decreasing function, because then that means that the term after it is smaller than the term before. And if it's greater than 1, then the term after is bigger, and therefore we have an increasing function. And we know for derivatives, if the derivative of the function is negative, then that function is decreasing, and if the derivative of that function is positive, then that function is increasing. So what you want to do is, when you have these problems that you want to show that a sequence is monotonic, you want to try to pick the easiest one. So in this first example, the easiest is going to be the difference test, the algebraic difference test. Because if I want to know what s sub n plus 1 is, I'm going to add 1 to each of those. So I get n plus 1 over n plus 1 plus 1, which is n plus 1 over n plus 2. And then if I subtract those, and then we get a common denominator of n plus 2 times n plus 1, and we multiply through in the top, we'll end up with n squared plus 2n plus 1 minus n squared minus 2n. So everything cancels on the top except for the 1. This is going to be greater than 0, so increasing. Again, because we know n is positive numbers, this will have to be a positive number, and therefore the s sub n plus 1 is bigger than s sub n increasing function. The easiest test for this second example is going to be the ratio test. So that's going to take s sub n plus 1 over s sub n. So we have e to the n plus 1 over n plus 1 factorial, e to the n over n factorial. In fact, anytime you have a factorial, the ratio test is going to be the easiest test to do, because then now I can pull out that e to the n plus 1 over e to the n and multiply it by n factorial over n plus 1 factorial. Well, n factorial over n plus 1 factorial is just 1 over n plus 1, because if we think about factorials, the only difference between these two is that this has an n plus 1 in it. So it's like having n plus 1 times n factorial over n factorial, and that's where we get, or n factorial over n factorial times 1 over n plus 1. That's why we get this here. And then this is just e. So then that leads us to e over n plus 1, which is less than 1, because for all of n is greater than or equal to 2. So after the first term, this is a decreasing sequence. And then if we do part C, the easiest one for that one is the derivative test. Again, we didn't want to pick the derivative test for this one because we would have to use the quotient rule, and the algebraic difference was much easier. Anytime you have a factorial, the ratio rule is going to be the best choice, because this ratio is going to equal this right here. So you can always do that. And then this one is good for a derivative test, because the derivative, if we call f of x ln x, the derivative is 1 over x. And so we know that 1 over x is positive whenever x is greater than 0. So f is an increasing function. And therefore the sequence is also increasing. So those are 3 tests that you can use to determine increasing or decreasing. It doesn't help you determine whether it's non-increasing or non-decreasing, but it helps you determine increasing or decreasing in a sequence. And all bounded monotonic sequences converge. So if you can show that a increasing function is bounded from above or a decreasing function is bounded from below, then you can say that that sequence converges.